Valence bond theory. In previous videos, we have seen two theories of bonding in coordination compounds, Werner's coordination theory and effective atomic number rule. But with the advances in theories of chemical bonding, three modern theories of bonding in coordination compounds have been developed. These theories are valence bond theory, crystal field theory, and molecular orbital theory. In this video, we will discuss valence bond theory of bonding in coordination compounds. Valence bond theory was given by Linus Carl Pauling. In a coordination compound, there is a central metal ion and surrounding ligands. This theory takes into account the hybridization of vacant orbitals of central metal ion. Central metal ion, usually the transition metal ions, have s, p and d orbitals. D orbitals are usually partially filled in case of transition metal ions. In these metal ions, empty d orbitals of the metal ion and outer sp orbitals hybridize to give a set of hybrid orbitals, and these hybrid orbitals arrange themselves in specific geometries depending upon the type of hybridization. D orbitals of the metal ion may be inner d orbitals or outer d orbitals. Ligands must have at least one lone pair of electron, as we have already discussed in ligands, and when this hybrid orbital containing one lone pair of electron overlap with the hybrid orbital of central metal ion, a coordinate bond is formed, and the interaction between a metal ion and a ligand is considered as Lewis acid base reaction, in which ligand is considered as Lewis base and metal ion is as Lewis acid. Now, in this slide, you can see a metal with its d orbital. These d orbitals are empty when a ligand is present. It donates its lone pair to the empty orbital of metal ion and a coordinate covalent bond is formed. This is how central metal ion makes bond with the group of ligands surrounding it. Now, let us see how a coordinate bond is formed. In central metal ion, there are inner d orbitals and outer sp orbitals. In some metals, outer d orbitals are also used to make bond with ligands. First, the available empty d orbitals on the central metal ion get hybridized to give hybrid orbitals, and these hybrid orbitals overlap with the filled orbital of a ligand containing a lone pair of electron, and this is how a coordinate bond between a central metal ion and ligand is formed, in which ligand donates its lone pair of electron in the empty hybrid orbital of central metal ion. Now let's see the different types of hybridization resulting in the different geometries. Metals form different coordination compounds of different coordination numbers. Usually in metals, inner d orbitals, outer s, p and outer d orbitals are used, in which the orbitals hybridize to give different types of hybridization. In case of a compound of coordination number 2, the two hybrid orbitals are required. And with coordination number 2 in a complex, there is sp hybridization. One s and one p orbital is used to make bond. First, these two orbitals get hybridized, and these two orbitals arrange themselves in linear manner, and with these two hybrid orbitals, ligand orbital overlap to make bond. When the coordination number 3 in a complex, the hybridization is sp2. One s orbital and two p orbitals are involved. These three orbitals arrange themselves around central metal ion in trigonal planar arrangement. So the geometry of a complex with sp2 hybridization is trigonal planar. A complex of coordination number 4 requires 4 hybrid orbitals. In one type of hybridization, one d orbital, one s orbital, and two p orbitals are used to get hybridized orbitals, and these 4 hybrid orbitals, which are dsp2 hybrid orbitals, arrange themselves around central metal ion in square planar arrangement. And the geometry of a complex with dsp2 hybridization is square planar. There is another type of hybridization with coordination number 4, which is sp3 hybridization, in which 1s and 3p orbitals are used, but the arrangement around the central metal ion in this type of hybridization is tetrahedral, and the geometry of the complex would be tetrahedral in such a complex. In a complex with coordination number 5, 5 orbitals are required, and the hybridization is dsp3 hybridization. One inner d orbital and s orbital and 3p orbitals are used to get hybrid orbitals, and these 5 hybrid orbitals arrange themselves around central metal atom in trigonal bipyramidal geometry or trigonal pyramidal geometry. In a complex with coordination number 6, 6 hybrid orbitals are needed, and when the two d orbitals, which are inner d orbitals, are used, and one s and 3 p orbitals are used, these 6 orbitals arrange themselves around central metal ion in octahedral geometry. Such a complex is known as inner complex because in this hybridization, inner d orbitals are used. In coordination number 6, complex may also, a metal can also use its outer d orbital depending upon the electronic configuration of the metal ion and the availability of d orbitals. Metal uses its outer d orbitals. The hybridization is sp3d2 and the geometry of the complex is octahedral, and these complexes are known as outer complexes. Here in this table, complexes of different geometries or shapes with different hybridization are given. In linear complexes, because there are only two hybrid orbitals in these complexes, there are two ligands bonded to the central metal atom. The examples of linear complexes are dichlorocuprate, diamino silver, dichloroaurate. In trigonal planar geometry, the hybridization, as we have already discussed, is sp2 hybridization, and there are three ligands bonded to the central metal atom in the given example. In square planar complexes, dsp2 hybridization, and there are four ligands bonded to the central metal ion, and the orbitals involved are 1d, 1s and 2p orbitals. In tetrahedral geometry, the hybridization is sp3 in the examples of tetrahedral complexes given here. Similarly, in trigonal bipyramidal complexes, the hybridization is dsp3 and the example of this complex is pentacarbonyl iron. In complexes where coordination number is 6, the two types of hybridizations are d2sp3 and sp3d2, and in both the cases the geometry of the complex is octahedral. In the examples of these both types of complexes, inner and outer complexes given here in this table. Here in this slide, these are the geometrical arrangements in different complexes around central metal ion. This is linear complex in which two amino ligands are bonded to the silver ion. In tetraamino complex of platinum, platinum is at the center and four amine ligands are surrounding central metal atom in square planar geometry. This is tetrahedral complex of a zinc in which zinc is central metal ion and the four ligands are surrounding this metal tetrahedrally. This is an example of octahedral complex of cobalt with 6 ammonia ligands. Now, let us see formation of some coordination complexes. This is an example of octahedral complex of chromium. Atomic number of chromium is 24 and its electronic configuration is 3d4 4s2. Chromium is in +3 oxidation state in this complex and electronic configuration of chromium cation is 3d3. When this metal ion forms complex with 6 ammonia ligands, first its inner 2d orbitals and outer s and 3p orbitals get hybridized to give d2sp3 hybrid orbitals. These 6 hybrid orbitals arrange themselves around central metal ion in octahedral geometry. In these octahedrally arranged hybrid orbitals, 6 ammonia ligands donate their lone pairs of electrons and an octahedral complex is formed. In this complex, central metal ion is present at the center of the octahedra, and 4 of the 6 ligands surrounding central metal ion are present on one plane in square planar arrangement, and the remaining 2 ligands are present above and below the square plane. This is an octahedral arrangement in a complex. This is an example of inner complex because in hybridization, inner d orbitals are used. In this complex, there are 3 unpaired electrons which are present in 3d orbitals which are not involved in hybridization. When there are unpaired electrons in a complex, the complex is paramagnetic. This is the same complex we have seen the formation of hexammine chromium complex. In this complex, the inner 2 d orbitals are used. The electronic configuration of this complex is such that there are always 2 inner d orbitals available for D2sp3 hybridization, but there are metal ions in which there is no availability of inner d orbitals, or the outer complex are formed. How and when the outer complexes are formed, let us see in some other examples. This is an example of octahedral complex of cobalt. Electronic configuration of cobalt atom is 3d7 4s2, and cobalt metal is in tripositive cationic state in this complex, and the electronic configuration of cobalt cation is 3d6. When in formation of this complex, 6 amino ligands approach the central metal ion, the 2 of the 4 unpaired electrons present in 3d orbitals are forced or pushed inwardly to get paired with the inner 2 unpaired electrons, making 2d orbitals available for the hybridization. And the hybridization in this complex is D2sp3 hybridization using the inner 2d orbitals. After hybridization, 6 hybrid orbitals are formed in which 6 ammonia ligands donate their lone pairs of electron in the hybrid orbitals, making this complex. Because there is no unpaired electron in this complex, this is an example of dimagnetic complex. And because the inner 2d orbitals are used in hybridization, this is inner complex. When there is no unpaired electron in a complex, the complex is also known as low spin complex. There is another example of cobalt complex, hexafluorocobaltate. In this complex, cobalt is surrounded by 6 fluoride ligands, and the electronic configuration of cobalt cation is 3d6, and the 6 electrons are present in 3d orbitals, in which 4 of the electrons are unpaired. when 6 fluoride ligands approach central metal cobalt ion, the hybridization takes place using 1s, 3p and outer 2d orbitals, and these 6 hybrid orbitals arrange themselves around central metal cobalt ions, and in these hybrid orbitals 6 fluoride ligands donate their lone pairs of electron. Unlike in the previous example, another example of cobalt in which the ligands are ammonia ligands. In presence of ammonia ligands, the unpaired electrons were forced to get paired, whereas in this case, the unpaired electrons remain intact and the outer d orbitals are used for the hybridization. Such complexes are known as outer complexes because outer d orbitals are used. Because there are 4 unpaired electrons in this complex, this is paramagnetic in nature and is known as high spin complex. The geometry of this complex is octahedral. There is no effect on the geometry of the complex when the coordination number is 6, whether the hybridization is D2sp3 or sp3d2. In these two examples of complexes, the central metal ion is same and the oxidation state is also same. The only difference is the difference of ligands. In first case, in hexaamine cobalt complex, 6 amine ligands cause the pairing of electrons and cause the formation of inner and low spin complex, whereas in second example, fluoride ligands cause outer complex and forms high spin complex. So these are the ligands which determine the type of complex, whether it would be inner complex or outer complex. In the formation of octahedral complexes, we have seen two types of complexes are formed depending upon the type of d orbitals used in the hybridization. Outer complexes are known as high spin complexes because of the presence of unpaired electrons, whereas inner complexes are known as low spin complexes because of the less number of unpaired electrons or zero number of unpaired electrons. Ligands determine which type of complex is to be formed. Some ligands have tendency to pair the electrons and result in the formation of inner orbital complexes or low spin complexes. These ligands are known as strong ligands or strong field ligands, whereas there are some ligands that cannot pair up the electrons and results in the formation of outer orbital complexes or high spin complexes. These ligands are known as weak field ligands or weak ligands. You have already seen in the previous videos that there are different types of ligands. These ligands are arranged in the increasing order of their strength in a series, and this series is known as spectrochemical series. In this spectrochemical series, ligands are arranged depending upon their strength, which is derived from experimental data. Here in this series, the weak field ligands are starting from iodide to bromide to sulfide and goes on. The strength of ligands keeps on increasing from iodide to carbonyl. Carbonyl is the strongest ligand in this spectrochemical series. In this series, En stands for ethylene diamine, and next is bipyridine, then phenanthrolane. Complexes of coordination number 4. This is an example of nickel complex ion, tetrachloronickelate. Nickel is the central metal ion and it is in +2 oxidation state in this complex ion. Nickel has 8 electrons in its 3d orbitals and outer 4s and 4p orbitals are empty. In presence of 4 chloride ligands, these outer 4 orbitals hybridize to give sp3 hybridization. These 4 sp3 hybrid orbitals arrange themselves around central metal ion in tetrahedral geometry. In these 4 hybrid orbitals, 4 orbitals of ligands overlap to make coordinate bond and a tetrahedral complex of nickel is formed. In this complex ion, nickel has 2 unpaired electrons in 3d orbitals. So this complex is paramagnetic in nature. This is another example of a tetrahedral complex ion, tetrahydroxozincate ion. In this complex ion, zinc is in di-positive oxidation state and it has 10 electrons in 3d orbitals. So outer s and p orbitals are available for the hybridization. These 4 orbitals hybridize to give 4 hybrid sp3 orbitals in which 4 hydroxyl ligands overlap with their filled orbitals and make tetrahedral complex. As in this complex there is no unpaired electron in 3d orbital, so the complex is dimagnetic in nature. In this complex of nickel, nickel metal is in di-positive oxidation state, and in this complex, in presence of 4 cyano ligands, these ligands cause the pairing of 3d electrons and make available d orbitals for dsp2 hybridization. These 4 dsp2 hybrid orbitals arrange themselves around central metal ion in square planar geometry. In these 4 hybrid orbitals, 4 cyano ligands orbital with their lone pairs of electron overlap to make coordinate bond. As there is no unpaired electron in 3d orbitals, this complex is also an example of dimagnetic complex.